Hello everyone. In our last video, we have talked about LIG, but how to tell that our LIG is actually good or not. So there are basically two tools, which is called Raman and another one is sheet resistance. In this video, we will talk about Raman spectroscopy and sheet resistance, and by these two things, we will comment on if our LIG is good or not. So let's get started. So let's start with the Raman first. So what is Raman spectroscopy? The philosophy of Raman is actually not so much fancy, it actually simple. So first of all, we hit a laser on the sample, and when a laser hit on the sample, it actually bounce back with kind of the same energy. But there are a tiny bit of lights, for example, 1 in a million, emits in slightly different energy. Actually, Raman actually measures this kind of scattered light and measure the scattered light and create this kind of graphs. The thing is, different carbon materials which is present in this structure like graphene, graphite, plastic, they all give different kinds of uh, emitted light with a different energy variation. So we'll get a different kind of this kind of graph. So actually Raman tells us what kind of carbon we actually made, what kind of carbon actually present in our the substrate, not just guessing. So we can see this is a typical Raman spectroscopy, and first let's discuss about the G peak. So G peaks come around at like 1580, and G stands for graphite. These peaks tell us about the perfect honeycomb lattice, this peak, and the honeycomb structure I showed in the graphene video. So if the peak is strong, it has a very high intensity, then we can say that it is a very ordered graphene. Okay, so the next one is like D peak. So D peak, what is resembles? D peaks appear where the lattice has holes, edges, disorders, and more defects. So if there is more defects, then this peak will be more intensified. We can see the intensity is not so strong, so we can say in the LIG structure, in the substrate where creating the LIG, there is defects. Obviously there is defects, but not much defects there is present on. Another is G prime peak, which is we can also call it D peak. So what actually 2D peaks tells us about? This one tells us about the number of layers. Single layer graphene gives sharp peak, few layer graphene gives broader peaks. For LIG we actually got a few layer, few layer graphene, so this peak will not be so sharp. This will be kind of a broad version, this kind of things. So let's move to the next slide. So here we can see a magic ratio which is called IG ID IG ratio. So what is actually that? So obviously it's a ratio, so it can be low, it can be higher. So if we talk about the low ratio like 0.1 to 0.2, that means the Z peak is way bigger. So if the G peak is way bigger, so the D peak is smaller, then we'll get a low ratio. So we can say that there are few defects, so that we can produce a high quality graphene. But if the ratio is higher than 1, so we can say that it is ID dominating. So the intensity of D peak is more, and even more than the G peak. So we can say that obviously there are more defects than the stable graphene hexagon structure. So there will be more defects, and that will not be useful for good conductive use or something. But in LIG obviously we need some defects, and the LIG is actually, if the ratio is actually between the 0.5 to 1, it is considered a good LIG. So we have a basic idea on Raman, how it looks like. The another is sheet resistance. So what is sheet resistance? We are prepared the LIG. Okay, this is the LIG substrate on which LIG is formed. So what's the resistance of this sheet? Obviously, we know that resistance is connected to conductivity. So the resistance, if the resistance is higher, then the conductivity will low. So we can comment that the LIG is good or not. So unlike other resistance, it is measured in ohm per centimeter, so it's not just ohm. And it's called it's also basically calculated by Ohm's law, and that's the typical equation by which the sheet resistance is measured. This is a constant value. It's comes from a geometric factor, but we are not discussing it now. So actually we are measure the voltage across the sheet, and we divide it by the current, and by Ohm's law we know that's how actually we measure the resistance. So that's the thing. So but there are actually two ways we can measure this. So we'll discuss both ways, and we'll suggest which way is better. So the two ways I have already mentioned, one is 2-point probe system, one is 4-point probe system. We can see there are two probes or two needles, and there are like four needles. So by the number of needles we call it 2-point probe system or 4-point probe system. So nowadays and almost every time we have to use 4-point port system because it eliminates the contact resistance problem, which is actually a very prominent problem we can see in 2-point probe system. So let's discuss about the 2-point probe system first. So first we talk about 2-point probe system. So first of all, we have to know that what our voltmeter actually measures. See, it measures the voltage drop, and voltage drop depend on the current we are passing through the wires, and also the resistance of the sheet, and if there is any other resistance present. So there are more than the sheet resistance, there are resistance between the contact point of the needle and the surface of the substrate, and also this point, this. So this R is not basically only the R or resistance of the substrate. These are actually the resistance of the LIG, the resistance of the contact point of this probe, and the resistance of the contact point of that probe. So the voltmeter measures the voltage drop, uh, you know uh, like I into R, but the R is not only R LIG. So the voltage drop is basically much more, right? So if the voltage drop is much more, if I divide V with the current we are passing through, then obviously the sheet resistance will be so much higher. So it will not give you the correct sheet resistance because it already considering this kind of contact resistance. And there is another problem with this kind of contact resistance is it depends on how hard you press the probe into the surface, if there is oxidation on the surface, if you touch the surface. So it's a very sensitive issue. So for this kind of contact resistance we are getting more voltage. So as we are getting more voltage, we are getting more sheet resistance. So that's why we actually don't use the 2-point probe system. But with 4-point probe system, it is unaffected by such contact resistance. So there are actually four probes situated at the equal distance. We can see the S distance. The outer two probes, they basically measures the current, and the inner probes measure the voltage. And the voltmeter here is we use has like millions of ohms of resistance. So there is almost no current passed through this because there is much resistance. So there is negligible amount of current is passing through. So if there is negligible amount of current passing through on these probes, so no matter how much contact resistance we are getting here, actually not affect the voltage, right? See this equation, V is equal to IR. So I is equal to like tends to 0. So no matter how contact resistance this two probes actually gives us, it doesn't affect the voltage drop here. So this voltage drop is actually dedicated to only uh, voltage drop due to this sheet resistance, not the contact resistance. So we are getting a real voltage drop, which is basically for the resistance of the substrate, and then we are dividing this I with with that voltage. So there is actually no contact resistance contamination. So that's why we are using 4-point probe system rather than 2-point probe system. I hope you understand this clearly. So obviously, if the sheet resistance we calculated with that equation is high, then we will get a very low conductivity, and if the low sheet resistance we have, we get the high conductivity. So Raman actually tells us which kind of composition we have, and sheet resistance tells us is it conductive or not. So by using those information about the defects, how much defects is presented here, if there is graphene structure or not, or it's just a burnt plastic, or if it's one layer but two layer or three layer, and by these kinds of things we can comment if our we can thumbs up that our LIG is good or our LIG is not good. So we can comment on this, right? So up to that we understand a lot of things. So you already know a lot about LIG that many people don't, and I also don't know many things. So please go tell someone, and I don't like to beg, subscribe, or like or something. So if you enjoy it, that's enough for me. Thank you. And I will be making some videos as per your request or any comment on my video ring, and maybe I will make a video of HER reactions, hydrogen reaction or something, or hydrophobicity or something. Let's see. Bye bye.